Welcome to another wonderful episode of the New York City Category Theory Seminar, Spring 2025. Emilio is giving his, I don't know, I think you and Ray are neck and neck. Who's going to give the most? Anyway, structured decomposition categories. Try to work with this. Hold on. And, okay, we'll show you the references in a minute. Sorry. Okay, sorry. Okay.
Of course, you are a reference.
You are. Okay, good. Okay, good. Emilio, take it away.
All right. Thanks, Nosen. So I gave a talk last semester about one of the papers I referenced over there. And so in some ways, the talk I'm going to give today is a prequel to that talk. Okay, so what happened was after I gave the last talk, I started talking with Ben Bumpus, who's the main person behind that paper, and I realized that there was a way to extend some of his results to a larger class of categories, and then we figured out that that could actually extend a lot of results with this paper, so I joined in on that project and we rewrote the paper here now, and it's quite different. So let me talk a little bit about some of the philosophy and ideas going into this. So if you saw my last talk, you'll remember that the idea there was that there are these computational problems that computer scientists and mathematicians really care about, but they're NP complete. So a lot of computational problems that people care about turn out to be NP complete, and that's a real bummer, right? But
this is the book with you had 8 different definitions of what a graph is.
yeah, right. So there's all different kinds of graphs, right? So yeah, so you have these computational problems, they're NP complete, but you don't give up. You say, okay, maybe my problem becomes polynomial time if I restrict to a smaller class of objects, right? So sometimes you can do this. So this is one of the ideas of parametrized complexity theory. And for us, we're going to think a lot about graphs. So by restricting from the class of all graphs, if we restrict to certain other classes of graphs, we can come up with polynomial time algorithms, polynomial in the size of the graph, right? So to do this, we use what are called width measures. So there's all these different kinds of width measures you can come up with, and then we typically restrict to classes of graphs with bounded width measure, okay? And this is something that happens all over the place in combinatorics and algorithmics, right?
Every finite graph has a bounded width measure, right?
Well, there's no actual definition of a width measure.
Whatever the measure is, though, right? Every graph is going to have a finite number.
Well, finite graph.
I mean, depending on how you define it. So the most popular and powerful, important of all of these width measures that you could consider is called treewidth. Okay, so treewidth, very vaguely, if you squint at a graph, how tree-like is it, right? So if we restrict our computational problem to the class of graphs that have bounded treewidth, a lot of these NP problems now become polynomial time problems, okay? So that's the motivation. The only problem is that lots of classes of graphs that people care about don't have bounded treewidth. So for example, the class of planar graphs does not have bounded treewidth. So for example, if I consider the class of all complete graphs, so a complete graph, we call them Kn. So this is the graph whose vertices graph with n vertices and every pair of edges every distinct pair of edges is every distinct pair of vertices are connected by an edge.
Or one simplex, one subset of simplex.
Yeah. Yeah, exactly. Are connected. So the class of these things doesn't have bounded tree width. And so the complete graphs look like I have K1, K2, K3, and so on. And so I'll also say for right now, when I'm talking about tree width, what I'm considering are called simple graphs. And we'll talk more about the different kinds of graphs we can consider. But for right now, I'm talking about simple graphs. So these are graphs with vertices and edges. I'm not allowed to have loops, and I'm not allowed to have multiple edges. Okay? Parallel edges, right? So planar graphs don't have bounded tree width. This is annoying because we want to solve problems on planar graphs and other classes of graphs. So people
K4 and on is not planar.
K4 and on is not planar, right? But there are other.
K4 is planar.
It's the next.
K4 is planar.
Yeah, that's right. It's 5 when you start getting across.
Everybody else has to go around. Right.
There are other things called like grid graphs. So these
What graphs?
grid graphs.
Yes.
So things like this. These, when you consider these also don't have bounded tree width. So anyway, so this has set up kind of a cottage industry in combinatorics and algorithmics where you come up with a new width measure, and hopefully that's bounded on larger and larger classes of graphs. So what you've seen over the last couple of decades is like this explosion of these different width measures. And they all have different properties and different things, and oftentimes how you actually construct them is very complicated. So the motivation behind this work, and also kind of the last talk, is to come up with some kind of formalism to understand these different width measures and to compare them.
Could you mention at least one other example of a measure other than the tree width?
Other width measures?
Yes.
Yeah, I mean, we're going to talk about a whole bunch of them.
Oh, okay, fine.
Yeah.
At least one example.
Yeah, we'll see other examples. Yeah, I just wanted to give a little bit of a motivation, and now I'm going to...
They are coming.
Yeah, I'm going to talk about things rigorously. Okay? So that's the idea.
I just want to make sure you didn't assume that I knew any other measure than a tree width.
I'm not even assuming you know what tree width is. Okay? So let's get started. So first of all, we're going to let GR denote the category of simple graphs. So, as I said, these are graphs without loops and without multiple edges. And a graph homomorphism is not allowed to crush edges. So I send vertices to vertices, and then I have to send edges to edges, right? So here I have like, here, I can send this edge to this one, this there, and then I can send 3 to C, right?
Very not topological.
Very not topological.
Geometrical.
So GR is going to be the category of simple graphs and these graph homomorphisms.
Wait a minute, so what happens, how do you go from 4 edges to 3 edges?
So what I can do is I can map this vertex and this vertex to this one.
Okay, so when you
and map 3 to C.
So okay, so both 2 and 3 go get crushed together to C.
Yeah, but what I'm not allowed to do is take this whole edge and crush it down to this point.
Yeah.
I'm not allowed to do that, okay? All right, good.
So then you have more than one edge between 2 vertically mapped, the edges must get mapped
So
together.
they're self-loop free.
Yeah. Okay?
No, but it's saying something, it's saying that, don't think of, a dot as, a zero-dimensional line. It's a totally different thing. You
Yeah.
can't-
Yeah, this is how combinatorialists think of graphs typically. Yeah, okay.
You usually think of a line as like an extended dot. He's not letting you do that. He says you can't map a line into a dot. A one-dimensional thing doesn't go down to a zero-dimensional.
I have a question.
Okay, yeah.
Is it right to define a tree decomposition to be of a graph to be a surjective map from a tree to the graph?
No. All right, so I'm gonna just call simple graphs graphs from here on out, right? So to every graph G, I'm gonna associate a category. I'm going to call it integral of G, okay? So this category has objects given by the vertices and edges. Of G. And then the morphisms are going to go from every edge, there's going to be 2 morphisms sticking out to the vertices.
You had this in the last one.
Yeah.
But I don't think you spoke of integral.
No? Maybe not.
So take this close maybe to kind of like category of parts.
So that means I have, say, a graph like this with vertices x, y, and z, edges e and f, then, and I call this g, then I'll have integral of g, we'll have x, e, y, and that edge is going to point towards the 2 vertices, like that. And so in the paper, we call this the barycentric subdivision. Okay? So this is a category, right?
What do you call it again?
Barycentric subdivision, right?
Why the arrows go that way rather than the exclusion?
Because to do that, you could just do op, right? So.
Can I answer why you call it integral? Is it a twisted category?
So why we call it the integral is there's something called the Grothendieck deconstruction, right? So the category of directed graphs is a presheaf category. So you can think of every directed graph as a presheaf. If you take the Grothendieck construction, or the category of elements of such a presheaf, you get a category that looks just like this. But then you're allowed to also have loops and multiple edges. Okay? Good. So, right. So if I have a graph, I get a category, and I call these guys, the vertices here, the bags. And then I call these guys here the adhesions. Okay? Right. So to every graph I associate that. I'm actually going to use this board. Is that all right, Nelson? So then.
That's totally generally replace the board.
Oh, okay, that.
Good.
So if I have a category, I call a structured decomposition in C a functor from the barycentric subdivision of some graph into C. Okay? And I also call the image of these things in the category the bags and the adhesions, right? And then if X is in C and the co-limit of D is isomorphic to X, I say that D is a structured decomposition of X. Okay?
Can we go back to Lou's question? Because he wanted just a tree, and your integral G is very much like a tree. He wanted, well, right? You said.
Well, I was just trying to wrap my head around the tree decomposition.
Yeah, we're going to talk about tree decompositions. Right? But here I haven't talked about any of that yet. I'm just saying to an arbitrary tree, I associate a category.
Arbitrary graph, you mean?
Arbitrary graph, I associate a category. Thank you. Okay?
So you're saying integral G is not necessarily tree-like?
So it doesn't have to be a tree decomposition, it can be a graph decomposition, or some other decomposition over some other.
Right, because for example, I could have this, and then I would have that, right? So that's nothing like a tree.
Right.
Right? Okay, so now let me give an example of a structured decomposition of a graph. This is going to be kind of silly, but it gets to kind of the heart of what's going on here. Say I have a graph homomorphism that takes this edge and places it here, and then I have graph homomorphism that takes this edge and places it here. This is a structured decomposition in the category of graphs. So this is a functor from this graph to the category of graphs, right? We see that because the vertices are these guys, and then I have the edge is here. And then when I take the co-limit of this diagram, I get this graph, right? That's pretty straightforward. So this is the kind of thing we're going to be doing, okay? All right, questions about that?
I remember that from the last time you taught. That was a good example.
Good. Okay, so now let me give some definitions. Just want to have this ready. Okay, so an SD category, SD stands for structured decompositions, consists of a category C and a class of graphs curly G such that for every structured decomposition with G in curly G, the co-limit exists. Okay, so it's very, very simple definition. It's just saying that I choose a class of graphs maybe the class we're going to consider a lot in this talk is going to be the class of trees. And I ask that every diagram that looks like that in that class has a colimit. Okay? So nothing really interesting here. Now, what we want to do...
So in particular, if the C was co-complete, it trivially would be this. But,
Yeah.
But the point is, it may not be co-complete, but it might just have these limits which are the only ones you care for.
Exactly. And the point we're going to see soon is that when C is the category of graphs, it's not co-complete.
Can you say that over, or he said it too fast, or whatever, I didn't see what he said.
Well, he's just saying if C is co-complete, it's
It's what?
an ST category for any class of graphs.
Trivial.
Oh,
trivial
because the colimits always exist.
Yeah.
Yeah.
Okay.
So,
So one second, so, and Ray, what did you say afterwards? And if, so if C
Well, but the point is, in the definition, the point is, if it's not co-complete, you know, all we care for is these colimits, so if it has these, and then you point out, you take graphs, in this sense, not the nice category to topos, but the one that the graph theory is called graphs. It doesn't have all colimits, but it does have these colimits.
This is a nice way of picking out like, a category with specified colimits.
Yeah, what is that certain goal? Oh no, more definitions.
yep, more definitions. So now, a spined SD category will consist of an SD category with additional structure. Okay? So it's going to be equipped with a filtration of essentially full subcategories omega called the spine, and by that I mean we have a bunch of essentially full subcategories and omega is the union of all of them.
Subcategories of G or of C?
Of C. G is not a category, it's a class of graphs. Okay? So C, what I'm doing is I take all these full subcategories and I'm going to take a filtration of them.
So this is your parameterized.
The parameter, exactly. Such that, did not leave myself enough room, such that we have two conditions hold. For every object X in C, there exists a monomorphism into an object W, and W is in omega. So that means for every object, it has a monomorphism into something in one of these full subcategories. And when I say essentially full, I mean that it's closed, each one is closed under isomorphisms. Okay? So that's condition 2. I mean, that's condition 1. Condition 2 says that for every n greater than or equal to 1, if W is in omega minus omega n minus 1, then there exists no monomorphism W into W prime, where W prime is in a smaller thing.
So if W only appears at stage N,
And it's not allowed to have a mono into something lower.
it can sort of like half appear at stage N minus 1.
Exactly, exactly. So the idea is going to be So before I get into the rigorous definitions, the idea here is that you imagine you have some object and you come up with this filtration and you say, okay, I want the smallest n such that this object has a monomorphism into one of these. I'm going to call that the size of the object. Okay? So this is going to be a way of associating a size to every object.
Just because say monomorphism, you mean monomorphism from the identity, morphs an object into that, or?
No, I have an object, x, and I'm saying, does there exist a monomorphism?
Never mind, I'm confused. Yeah. Yes.
And then this thing says that this size makes sense.
Okay, fine. Never mind.
And the closed-end isomorphism means if you have two structures that are isomorphic, you want them to be treated the same for your complexity.
Exactly. Okay, so let me give the main example we're going to talk about. So the main example we're going to discuss here is the following, where CG omega is the category of graphs, the class of trees, and then omega is going to be complete graphs. So let me explain what I mean by that. So omega n is going to be the set of all complete graphs m such that m is less than or equal to n.
This sounds familiar from your last talk.
Right? So now, when does a graph have a monomorphism into a complete graph? Right? So say I have a graph like this, I can always map it into the complete graph on 3 vertices. And in fact, if I have a graph on n vertices, I can always map it into the graph, the complete graph on n vertices.
So you're generalizing degree.
What was that?
You're generalizing degree in some sense.
Yeah, exactly. So the way we can think about it is that this is a filtration on the size of the vertices of graphs, right? So I have a mono into one of these guys if and only if my number of vertices is less than or equal to that, right? Okay. So I haven't yet said that this is a spined ST category. I have to prove that. Yeah.
But you have, do you know these filtered categories where any pair of arrows coming out eventually has a ceiling?
No, I don't know what that is.
It's sort of like this kind of filtration, except that this kind of filtration, except it's non-linear, so it can branch out. But the condition is there has to be something down the line where it rejoins.
So some sort of like in lambda calculus when you have the.
Well, church process.
Yeah.
I was thinking.
One second, so W member of omega n, that's just Kn in your case.
That's just Kn. And I want to make sure that K3 doesn't have a mono into K2, which it can't because otherwise it would crush vertices, right?
Makes sense.
Okay, good. Right. So now, so I still haven't proven that this is a spined ST category. There's content to saying that because I have to prove that for every structured decomposition where G is a tree, that the category of graphs has a colimit. Now it's trivial to see that the category of simple graphs does not have all colimits. Like one example would be this does not have a push out in the category of graphs, right? Because if it did, it would be something like that, right? But you're not allowed to do that in this category.
That category sits inside something which has all push-outs and.
Yeah, but I'm talking about this category.
I'm saying.
Yeah.
But this is the proper subcategory of it.
So the regular category of graphs is co-complete. Because
Well, it depends what you mean by regular category of graphs.
If you mean the topos, it certainly is.
Yes.
But it sits in there, but it doesn't have all, yeah.
if you think of it as a pre-sheaf, so then it is co-complete.
Sure.
Totally. But these are not, this is not a pre-sheaf topos.
Right.
This is not a very nice category.
Right, it's a subcategory, I think, which is not closed under code.
Right. However, this is a proposition. Proposition, if I have a category I and it's simply connected, if I is simply connected and I have a diagram D from I into C, and C has all pushouts, and C has all pushouts, then the colimit of D exists in C. Basically what we're saying is that when there's no cycles in the category loops, I can construct its colimit by taking iterated pushouts. Okay? So this is a nice proposition, and it turns out that while this category doesn't have all pushouts, it does have a special class of all pushouts. So another proposition, GR has all pushouts of monomorphisms. So that means
the reason why you messed up is you had two dots going to one dot.
exactly. So that wasn't a mono.
Yeah.
But if I have two monomorphisms like this, then the pushout does exist.
So that example that we gave earlier is essentially the only way you can go wrong.
Exactly. So this pushout exists. So that means that, oh, and I forgot to say something crucial. When I said structure decomposition, I always want the morphisms to land in monomorphisms. So the image of the morphisms should be monos.
Oh.
Okay, that's an important caveat I forgot to mention.
Okay, so you're going to say that a tree decomposition is now a functor from the integral of a tree to graphs.
Yeah,
Like that.
yeah.
Okay.
So basically what we're going to see is that if I have a structure decomposition in the category of graphs, then I'm going to have a simply connected diagram of monomorphisms. I know that the pushouts exist, therefore I can construct the colimit of any structure decomposition of a tree, right? Because trees are simply connected. And when I take the integral of a tree, that's also simply connected. Okay? So, corollary, I guess, is that this is a spined ST category. Is a spined SD category. Okay? So that's the main example we're going to be thinking about and trying to generalize. So now that we have the definition of a spined SD category, we want to come up with a notion of width. We want to associate to any spined SD category a width measure, because our goal is eventually to come up with a formalism where we can compare these width measures. So, definition. So suppose I have a spined SD category the size S of X of an object X in C is the smallest n such that X has a mono to W and W is in omega n, right? And to be an SD category, you have to have for every object a monomorphism to some object. So that every object has a finite size. Okay? Okay, good. So now, our first lemma. And now I'm going to start using this notation of gamma for the whole tuple here is a spined SD category. And I have a mono from X to Y. Then the size of X is less than or equal to the size of Y, which is exactly what you would want, right? And the proof is trivial because it says, suppose I have a mono into some object omega here, and omega, and W is in omega n, and then that means that the size of Y is less than or equal to n. Well, then I can just post-compose, pre-compose. Right? So, size is monotonic under monomorphisms. Okay, good. So that's size, and now from size we want to get the width measure. Okay, so given a spined SD category, gamma C G omega, and a structure decomposition where G is in the class of graphs. So we know that its colimit exists in C, so it means to be an SD category. We define the width. The width of the structure decomposition to be, we take the maximum over all of the vertices of the graph, and we take the size of the bag minus 1. And this minus 1 is an annoying convention from graph theorists that we'll talk a little bit more about. Okay?
The minus 1 inside or outside?
Like that.
It actually doesn't matter.
It doesn't matter. But
Can you explain? Okay, X is an element of V. What is V?
so G is a graph.
Oh, that's okay. Yeah, I know G is the graph.
G is a graph, and then VG is the set of vertices.
Oh, the vertices in the graph. Okay.
Right? So you imagine that, so let me give an example here. There's a nice example. Well, maybe, yeah, it's fine. I'll give the example here. So, well, actually, let's just do the example from before, right? right? So this was a structure decomposition of this graph, right? And the width of this structure decomposition is the maximal size of these two bags. So we don't care about the size of the adhesion. We know that the size of the adhesion is going to be smaller anyway in this case. But in this case, the width of the decomposition is 2, right? Because each of these bags have size 3. Does that make sense? Now,
If there were points, you would get width 0.
if there were points, you would get width 0.
By the funny convention with the -1.
Yeah, exactly. Okay? So this is the width of a decomposition. Now what we want to do is minimize over all decompositions. So if I have an SD category, nice. I have this right here. And X is an object in C. Then the gamma width of X is and we write that as like this. This is the minimum over all structure decompositions of X and the width of that decomposition. The width of every decomposition is finite. Might be infinitely many decompositions, but we can still take the minimum. That'll be finite. Okay? So this is now a legitimate invariant of the object, right? So to any object in a spined SD category, I can associate its gamma width. Yeah.
What's the gamma referred to? Is that the name of the SD?
Yes. Thank you.
You just have to enumerate all of those decompositions.
Well,
That's easy.
yeah. Right. Okay. So we've constructed for every spined SD category the gamma width, right? Good. So now, let's do a different example. We can consider the poset of n with its typical partial order. This forms a spined SD category. This forms a spined SD category of the form gamma. I can consider all graphs, and then I can consider the filtration to just be up to n. Right?
These are snake graphs? There's
just graphs. These are all graphs, right? So as a poset, this thing is co-complete. You always just take the maximum, right?
No, but n is a long snake, and boldface n, and small n is just part of it.
This is an object in here.
An object or anything less than it?
Well,
It's a set of objects.
So it's
Right.
So n and everything less than n.
Right.
Yeah.
one bump, two bumps.
Right?
Right. Sorry.
Okay. So if I take any finite diagram in this category, its colimit exists, it's just the maximum. Okay?
But it's not a graph. According to your definition, what does it even look like if I go from integral that graph to n?
I'm sorry?
What does it look like if I take a graph and just map from integral that graph into n? Because that is a, totally ordered thing, so I'm just going to sounds like so private that.
Right, so this is like a structure decomposition of 5, right? The co-limit of this thing is just going to be the maximum, right? And then the size of these two bags are going to be 3 and 4. So the size of 5 is 4. Okay.
The point is then a map from into a graph that just sounds like, okay, I'm just putting numbers on the different, the edges of nodes in a way that they're increasing along the arrow.
Exactly.
Then you can't do that, what if your graph has a cycle?
You'll allow cycles, remember?
You can allow cycles here, but it doesn't matter though.
Integral graph number has a cycle because the way integral was defined is the category of ends of that graph.
Is that
the graph which you have a cycle, integral graph number has a cycle.
Is that what fixes it, what Ray just said?
I don't understand.
Well, he even gave that example where we took a cycle and integral the graph was, remember, because the edges are all, all the things map into what was edges. Number 6 is once I take integral.
I could have like.
Do the numbers represent widths?
No, they're elements of ends.
The other
integers.
Let me.
Right, so here's a structure decomposition. Its co-limit is 5, right?
Okay.
And then its size is 4. Okay, so it doesn't matter if you have a cycle or not. All right, so this is just a very simple example. So I'm giving a bunch of definitions. I should be able to prove something about this. So the first thing we'll say is that the width of an object is always less than or equal to its size. Minus 1. I'll just say the gamma width of an object is always less than or equal to its size, minus 1. What's the proof? I also should have mentioned this. I always want G to contain the graph with just one vertex. Okay? So I always want that to exist. And then what do I do? For any object, I can take the structure decomposition given by that object. Right? So for any graph, or sorry, there's always a decomposition. I'm just going to say decomposition instead of structure decomposition from now on. There's always a decomposition of the form D, where I take this graph, that's just one vertex, and I put that inside of C, such that D of that is just X. And then what's the width of this decomposition? It's the size of the object minus 1, right? So we know that the width is always less than or equal to size. Yeah?
There's something confusing in the definition of tree.
I haven't defined tree width yet.
No, I'm not talking about you. The definition, it doesn't refer to the tree. It refers to another graph, how many vertices go to a vertex in the tree. It has nothing to do with properties of the tree directly.
The same vertex,
It's a map.
different
How many different it's approximately how many different vertices get pushed down to a single vertex of the tree. Okay, so that's confusing when I first learned it.
Okay, so here's another example of a spined SD category where I consider the category of finite sets. I consider the graphs consisting of all paths. Paths are just vertices and then one edge going on, right? And then I consider these finite sets of cardinality n, right? Now, the size of an object here is its cardinality minus 1, right? but its width, the gamma width is, but the gamma width of n for n greater than equal to 1 is 1. So let me explain why that's true. So suppose I have a finite set n, then I can consider this structure decomposition
I guess one thing worth prefacing is that in this example, take a path. Integral of a path is always a zigzag.
Yeah.
So I'm taking, so in this case, structure decomposition means I'm taking a zigzag inside my category.
Yeah, exactly.
Right? The colimit is zigzag.
And all of these maps have to be monos, right? So now this colimit gives me n bar, but each bag has size 1, right? So that means the gamma width of n is 1, okay? Because you can't get it any smaller. But the size is much, much larger though. See that? So the width is really getting at how can you decompose an object in your category, okay? All right, good. So now, another lemma. Well, actually, one more definition. Say that a spined SD category is a width category. A width category if the following condition holds. If for every structure decomposition, with colimit y, and every mono from x to y, the pullback, I have a whole diagram over y given by the colimit cocone of D. What I want to do is pull that whole diagram back, and I want that to be a colimit. The pullback of D, which let's call the mono here F of D, if for every decomposition and every mono, the pullback of D, this exists and is a colimit cocone. So this is a very important property in category theory. It's this idea of being able to pull back a colimit cocone and get a colimit cocone. Categories where this exists for any arbitrary map F and any arbitrary diagram are said to have universal colimits. Okay? The category of sets has universal colimits. Okay? All growth and decompositions have universal colimits. That's one of its defining properties. Okay? All right. The category of simple graphs has this property with respect to trees. Okay? So, So this is not super hard to prove, but lemma. So when I consider this spined SD category, it's a width category. So pullbacks, arbitrary pullbacks exist in this category. And whenever I have a monomorphism of graphs, and I take a structured decomposition of tree shape, I can always pull it back, and that'll be a colimit.
Again, if you move from graphs up to topos, well, that is universal. So what it's saying is that when I go to this subcategory with the graphs, I have messed that part of it up.
Exactly, yeah. Okay, good. So now, these are the main categories we're going to consider. So this property is really, really helpful, okay, in what we're going to do. So now, we're going to restrict to width categories, and now we can prove a nice result. Okay, proposition, given a width category, and a mono, the gamma width of X is less than equal to the gamma width of Y. Okay? And here's the proof. Let D be a minimal decomposition of Y. So I want a decomposition of Y that achieves the gamma width that exists. And then I pull it back along F, and now I have a decomposition of X. Right? And so that means that I'm going to have for every vertex here, I have dx, de, dy, and then you imagine there's like a whole bunch of stuff here, and that's over y. There's a colimit cocone here, and now I have x, and I have a mono, and then I have the pullback of each thing here. And this is a whole decomposition of X. Now, there's a really wonderful fact in category theory that says if you take a pullback of a monomorphism, it's also a monomorphism, which means that I get monomorphisms here, like that, right? So that means that the width of this decomposition is greater than equal to the width of this decomposition, because the size of this object has to be less than or equal to the size of this object. But this was a minimal decomposition. Therefore, this decomposition, for every decomposition, it'll be smaller. Okay? So FD is a composition. Then the width of F star of D is going to be less than the width of D, which is the gamma width of Y. And since the gamma width of X is minimizing over all decompositions, that implies that the gamma width of X is less than or equal to that. And you're done. okay? So that means that gamma width is also monotone with respect to monomorphisms, okay? All right, so we've talked about that.
Quick question.
Yeah.
F is basically the monomorphism for X and Y.
Say it again?
The F that you made, pull back the alone F is not. Yes, okay, I just wanted to double check.
Yeah, sorry about that. Okay, so now we'll finally talk about tree decompositions. So I'll give you the classical definition of a tree decomposition, okay? We're all good with this? I don't feel like going to that board. Of what? All right, so let me give the classical definition. So this is classical. Given a graph G, a tree decomposition xt consists of a tree t and a function x, which assigns to every vertex of the tree a subset of vertices of the graph such that, one, the union of these guys, so these are subsets of the vertices of the graph, we call these the bags. This should be all of the vertices. Two, for every edge, E in the set of edges of G, there exists a bag xt such that the edge is a subset on this graph. So I'm going to use this notation, which says if I have a subset of vertices of my graph G, then G square bracket is the induced subgraph. So this means take all of these vertices and all of the edges in G that connect them, okay? So to every bag, I have an induced subgraph, okay? And it says every edge has to be in one of these bags, okay? So you can't have an edge that's not contained in a bag. And then three, this is the hard part, given three vertices x, y, and z in the vertices of the tree, if y lies in between x and z, what do I mean by if y lies in between? Well, T is a tree, so given any two vertices, there's a unique path between them in the tree. So that means y either lies between them on that unique path or it doesn't. So that means if y lies in between x and z, I require that the bag at the intersection of the two bags lies in y. So the idea here is that you have a decomposition of a graph and you don't want these bags to get too far apart, okay? So this is the classical definition, and I'll put it there. And so the proposition is that if I have a tree decomposition, I can get a structure decomposition, right? So, given a tree decomposition, x of t there is a structure decomposition that takes this tree, goes into the graph, whose co-limit is g, and it's very obvious how you construct it. D of t should be a graph. We'll just give the bag. And then what should the adhesions be? It should be the intersection of the two bags. Okay? Now, given, and so that means, oh, I should have also said that we define width and tree width as before. So the width of this tree decomposition is the maximum over all the vertices in the tree of the size of the bag, minus 1. And then the tree width of a graph is the minimum width of all of its tree decompositions. And now they put this minus 1 here so that we have this fact that you have tree width 1 if and only if G is a tree or a forest. Okay?
So I would make
forest.
the tree width of the tree be 0. Right? It's like the distance away from the tree, right?
I don't know.
That's one, two.
Right. So, okay, so this is the classical definition of a tree decomposition. And then if you have a classical tree decomposition, you can get a structured decomposition. And the width of this decomposition is going to be the same here, right? And now, if I have a structured decomposition, I can get a tree decomposition from it. But what's the only thing that's going to ruin this from being a bijection is that if I take a structured decomposition, the adhesions might not be the intersections of the bags, okay? So if I take this, I get this tree decomposition, I go backwards, I don't get what I started with. Yeah. But what I get back still has the same width. So it doesn't actually matter. There's a tree decomposition, and vice versa. With the same widths.
Wait, so you don't have a one-to-one correspondence between such decomposition?
No.
In the two senses?
I don't have a one-to-one correspondence, but I have maps back and forth. So I have, I'll say, structured decompositions, and then tree decomps. I have maps like this, and both of these maps preserve the width. Okay? So, from now on, I can think of tree decompositions using structured decompositions. Because the width of the decomposition stays the same, that means that the tree width and the gamma width are going to agree. So that means corollary, for gamma equal to graph trees Kn, the gamma width of a graph is the same thing as its tree width. Okay?
I'm a little surprised by that they're not the same decomposition. Sort of decompositions.
Well, they are up to the adhesions.
Up to adhesions.
So you can include sort of extraneous stuff in the overlaps.
Exactly. Exactly.
Oh.
Well, you would have something smaller. You can have something smaller than the overlaps. But yeah, so like you can prove that like those adhesions, it's not super important what they are when you take the push out.
So,
okay.
I have a question. It seems like these tree decompositions, it's not merely that you use them to find a width, is an actual decomposition of the graph that you want to do particular things with. And so there's various algorithms, I imagine, that depend on you having such a decomposition. And so since your decompositions are a little bit different, do the algorithms sort of carry over, or do they? Yeah,
because what would I do? I take a graph, say I have one of these guys, I just take this one, and then I just do the algorithm there, right? Okay, so that's why we can do everything we do with this example here, because up to some unimportant ambiguity, structure decompositions and tree decompositions are the same thing. And I'll tell you, it's not so easy to prove. So I made it seem easy. It's not so easy because you have to, exactly. So you have to be a little bit careful when you consider these push-outs. You have to actually get into the set theoretic construction of them and make sure that when you take this thing, that it satisfies that annoying property that I just erased, right? That third property is annoying to check.
Okay, so it has to do
with the actual, how you actually do push-outs in this category of graphs. So there's content to this proposition.
The annoying property?
So there was this property that said if I have 3 vertices on the tree and one is in between the other 2, then the bags, the overlap of the endpoints, has to be contained in the middle thing.
So in other words, it's not enough to just have some push-outs. That the push-outs have to be done a very particular way.
Exactly, exactly. Yeah, so there's actual content to that proposition.
So both of these, there's a sort of category of elements in those decompositions. Is there a sense in which some kind of category of elements in the classical tree decomposition, you get equivalencies there?
I don't know what you mean.
I don't know how to formulate it, but it seems like if you have your category of elements in the push-out.
The category of elements of a pre-sheaf?
Yeah, over that default functor of your.
This?
Yeah.
This doesn't have a category of elements.
The source, what P was, P is a
this thing. Okay, yeah.
Yeah. I'm wondering if there's some relationship between that and some kind of corresponding picture over in the classical definition. Yeah. It's not a full.
Well, this is the tree that you're using in the tree decomposition.
Right. I have a thought that is not fully thought out, so maybe that's the problem.
Okay. All right, so let me give an example of a tree decomposition, a more interesting one. Okay, so here's my graph G, and then, huh?
I'm sorry. You actually compute it.
Right?
Yeah, okay.
What was that?
I think that's E. Okay.
Yeah.
Between the on purpose?
Yes. Okay, so here is a tree decomposition. So here's a bag, and then here's a bag, and then here's a bag, and here's a bag, and DGH is a bag, and I'm missing an I. Oh, this should be I.
Yes. Oh, maybe not.
There we go. That's a bag. Okay. So these can be a little bit weird. A lot of overlap.
Where one of the bags is a disconnected subgraph.
Yeah, you can have bags be disconnected. So.
Example in your back pocket by chance?
No. So now the width of this decomposition is 2, right? Oh, well, here's an easy example.
Okay.
Okay.
minus 1.
Huh?
It's 3 minus 1.
This one, yeah, this is 3 minus 1, so the width of this tree decomposition is 2. All right? Okay. Good. All right, so now let's talk about some other examples. How am I doing on time?
It's 8:20.
So not a lot of time, okay. Right, so that's the basic example. And we want to capture other examples of width measures from the literature. Now, one caveat to all of this.
Why did you leave out the line from PDF? What do you get out of that?
It's just an example.
Oh, you could have put it in and it would have worked too?
Yeah. I want to make it a little bit more interesting. I don't know. So one thing I want to say right off the bat is that these structure decompositions are very heavily tied to the structure of the category, right? Because it's involving colimits. And if you read about width measures in combinatorics and algorithmics, not all of them really have this kind of flavor of depending so heavily on the structure. So right off the bat, I'll say that we do not get a lot of width measures using this technique, but we do get a handful of them, okay? So there's something interesting going on between when a width measure really digs into the structure of an object and when it doesn't. And I don't understand what that difference is or how you even know.
What are some of the examples of width measures that don't?
Oh, that don't? I'll talk about those more at the end, but there's things like rank width and clique width of graphs. And I don't know if those can be represented using a spined SD category or not. There's also hyper tree width of hypergraphs, which I tried for a very long time to get into this formalism, but it does not work. And also any width measure that doesn't have this monotonicity under monomorphisms, you know, can't be represented using a spined SD category. And there's plenty of width measures that don't satisfy that. Okay? So temper your expectations. Math isn't that kind to us all. All right, so let me do an example. Yeah, exactly. Exactly. Well, actually, before I give the examples, let me do one more construction. So, if the universe was really kind, we would be able to come up with some formalism where every width measure in the world has some, you know, associated category and width measure. And then what I would want to do is compare these width measures with a functor, right? So I'd have two categories and their associated width measures, and I would have a functor that somehow gives me a comparison between their width measures. So this is the version of that. So given spined SD categories, gamma and gamma prime with omega, a subset of omega prime, with G, a subset of G prime, a width functor F from C to C prime is a functor such that 1, for all x in C, the size of f of x is less than the size of x. So f can only decrease the size of the objects. And 2, f preserves colimits of structure decompositions. So that's why I want G to be a subset of G prime, because I want, if I take a diagram of this shape and I push it forward, I want that to also have the colimit. Okay? So now I have a way of mapping between two structured decomposition categories. And I'll skip the proof of this next result, but proposition, if I have given a width functor like this, then the gamma width of f of x is less than or equal to the gamma width of x. Okay? So this is a very quick way of telling when you can compare the gamma widths between two things. Okay? All right. So that's that. We have one example of a spined SD category that's interesting, and that gives tree width. Let's talk about some other examples in the literature. So another one that people really like is called path width. So let me kind of try and keep track of these examples. We have, I'll call it gamma GR, or maybe gamma TW, is graphs, trees, and KNs. Another thing people really care about is path width, and you can imagine what that would be. Instead of considering all trees, we consider only paths and KNs. And then the gamma width of this is exactly path width. Okay? So this is another invariant that graph theorists really care about. Another invariant.
And you're not erasing trivial implies because paths are trees and we're keeping the
Exactly.
measures thing.
So you get immediately that there's a width functor from gamma path to gamma tree width, and that immediately implies that the tree width of a graph is less than or equal to its path width. And this is, of course, already known, but it's nice to be able to formulate it in a very quick way. Okay? Okay. So now let's talk about a different example. So there's something called co-tree width, which is another one of these width measures, and I'm not going to motivate all of these width measures. You can always just think whenever I talk about a new width measure, somebody at some point said, oh, tree width isn't good enough. Let me come up with something that works, right? Okay, so now let's consider this category. GR bar has simple graphs as objects. But now the morphisms are different. A map from G to H is a function from the vertices to the vertices such that if I have an edge in the image, then I have an edge, this is an edge in H, then this is an edge in G. So for example, this is not a map in this category, right? Because it says that if I map these guys into here and there's an edge here, there had better have been an edge in the beginning. Yes. Yes, they do. So we call this a reflexive graph homomorphism. Reflexive graph homomorphism. Okay. Now there's a functor that takes a graph to its complement graph. So
showing the point is doing these simple graphs with 0, 1 edges.
exactly. So
Well, it's only well defined. If he's doing his graph, the edge set between two vertices is either 0 or 1. So I can have a complement with 0, like 1 and 1 by 0.
right, so this, if this is my graph G, then G bar is this graph.
Because you're taking complementation, then
Oh,
you're
this is just literally like flipping light switches.
Exactly, exactly. And then proposition, this functor is an isomorphism. The complementation functor is an isomorphism, and its inverse is itself. Okay? Because this functor is an isomorphism, we know that this thing has all colimits that this thing has. Right? Because they're isomorphic categories. So that means we can ask, is this thing a spined ST category? And it is. So, so then we get a new example, gamma, I'll call it treewidth complement, and this takes.
Oh, wait, now this is the first nice category theoretic fact I've seen about your GR category.
Yeah, yeah. So now I consider this complemented graph category, I consider trees, and instead of taking KNs, I take their complements. What's the complement of a complete graph? Discrete graphs.
So it seems like you can generalize this to path width as well and get a co-path width.
Yeah, yeah, totally.
You know.
Yeah, definitely. And the gamma width here is something that's already understood in the literature.
Co-path width isn't that interesting, is it?
It is interesting, actually. Yeah, it's used in algorithms, in algorithmics, yeah.
So clicks that are missing edge. Interesting.
Yeah, my collaborator Ben Bumpus, he's the real expert on this stuff. But yeah, so complemented tree width, like it allows for more algorithms for like dense classes of graphs. So yeah, so then if I take the complemented tree width, which is just the gamma width of this thing, this is exactly the tree width of its complement. Okay? And the way you see that is noticing that I have width functors back and forth, right? So that's how you get that.
A question. You have these different decompositions and these different widths. And are they each sort of tied to different algorithms as the case could be, or is there like are they sort of sometimes the same algorithm just with a different decomposition? Or how does that work?
Or are they associated with a different NP-complete problem?
All of the above. So any sort of reasoning you might think of, somebody's come up with a width measure for that reasoning. Whenever tree width doesn't work, somebody has to come up with a new width measure to solve their problem. Exactly. So you have just an unbelievable amount of these width measures, styled for every problem. They're complete, like tons of them are ad hoc. You know, it's.
I was more wondering if there's like a machine in some sense where you can come up with a new SD category and all of a sudden you have an algorithm or a number of algorithms you can just plug in and see what they do? Something interesting.
Well, no, but in my last talk, I talked about how if you can write your decision problem as a sheaf on the category of graphs or on another, SD category or something like that, and you can solve it in polynomial time on the bags, then you can get a parametrized algorithm on the whole thing. But let me not get too into that right now.
Without getting into it, but does that carry over to this general set?
So we haven't like tried to work to like make any special kind of things, right? But all of the stuff that you needed to make that work works once you in this framework.
That's what I wanted to hear.
Yeah.
Because the point is, yes, the idea is that if you have one advantage of doing categories, then I can do what you did in the last talk.
Exactly.
Really, it's 8:35, so just keep going.
How long do I have?
Minus 5 minutes.
Minus 5 minutes, okay. All right, in that case, let me just run through some examples here. Yeah, okay. Well, yeah, maybe I won't talk in too much detail about them. But for example, there's something called the independence number of a graph. Every graph, you can consider their independent sets. Independent sets are vertices such that no two of them have edges connecting them. Okay, and you always want to know, like, what is the biggest independent set in your graph? It's a very common problem. So then you can come up with...
Is that the one that's dual to clicks?
Is that the one that's dual to clicks? I think so. Yeah.
It's the flip thing. It's called click. The one and then the complement are called independent.
So you can get a SD category that has tree independence number as its gamma width. So this, and it actually, call it alpha, and you actually have to use this category for it. So you do trees, and then instead of discrete, you use omega alpha, and these are just graphs with tree independence number less than or equal to alpha. So then you can get the tree independence number, you get complementary tree width, path width, tree width. You can also do the same game with hypergraphs, and you can talk about hypergraph tree width. So get hypergraph tree width. So this is a category of hypergraphs, trees, and then these are like the complete versions of hypergraphs. I'll just write KN again. And what's really cool, and this took me quite a while to figure out, is that there's this functor from hypergraphs to graphs. So let me just say what a hypergraph is for people who don't know. So a graph, you're only allowed to connect two vertices. In a hypergraph, you're allowed to connect finitely many.
How does it differ? How does it, or does it differ from simplicial complex? Sounds like I've heard something
from a simplicial complex. A simplicial complex is a hypergraph such that every subset is also an edge. Okay, so like if every thing there was, okay, that would be a simplicial complex, right? So this is a hypergraph. I have a category of hypergraphs. There's a construction that's really well known in the literature, and it's called the Geisman graph.
Came to...
Yeah, Geisman. And what this does is it takes the same vertices here and then it gives a clique or a complete graph for every edge here. Okay, so this has been known forever, but what's not been known forever is how to make this into a functor. Okay? Because the normal morphisms of hypergraphs allow you to collapse edges, hyperedges. That means that you don't get a functor to the category I've been considering of GR, because you're not allowed to collapse edges. So typically what you do is you take a different category, but I really wanted a functor into this category. So what are the correct morphisms here? You define the homomorphisms to just be maps on the vertices, and you have to take an n-edge with n many vertices, to an n-edge. So you can collapse two n-edges together, but you can't take an n-edge and squish it into a smaller thing. Then this becomes a functor, and furthermore, it preserves push-outs of monos. And that means you get a functor of, you get a width functor between hypergraphs and their tree width and graphs and their tree width. And so that immediately implies that the tree width of the Geifman graph is smaller. And you can actually prove very easily that that the other thing holds. So these are actually inequality. Okay, and that's very well known. All of this stuff is very well known, but being able to prove it like this so slickly is really nice.
Can I ask a question about hypergraphs?
Yeah.
Is there some reason people get so structured in this by bipartite graphs?
Well, I mean, it's easier to reason about them like this.
Okay.
Right? So that's hypergraphs. And then there's two other things that come up in the literature. I'll just say it in words. There's something called layered tree width. So here you take a graph and you give it what's called a layering, which means that you have to be able to chop it up into pieces and have only edges in between the pieces and in the bags. You're not allowed to like you can have like this, but you're not allowed to have like that. So this is a layering, and then there's something called layered tree width, and then you can get an ST category structure on that. It doesn't give you layered tree width on the nose. It gives you, for every fixed graph, if you look at the category of its layerings and you take the ST structure on that, that gives you the layered tree width of that graph. So it's almost exactly the same. And then there's something else called H tree width, where it augments the tree width a little bit. So we get a couple of examples from the literature, but this is really just kind of a first step in this direction. And we're hoping to be able to extend it to more examples. And I'll stop there.
Because you were saying, nice thing about this was that you were saying you can't get all your, there's tons and tons of widths that you make by the hop.
Yeah.
Not all fitness, but the nice thing is if you can't fit in here, then we can fit in the story of the sheaves from your previous talk into it, whereas with that hop thing, maybe I don't have anything like
Exactly, exactly. Yeah, so the hope is that we can kind of build a whole kind of formalism here.
At the point, if you don't get all of them, you're not going to get every half one, but you get at least enough interesting ones, and the benefit is when you do, well, now you've got the whole story with the sheaves, so I can actually know how to systematically get algorithms, etc., as opposed to just saying I have a measure and I don't know how to prove any graph theory theorems with it, or make algorithms or do anything further with it.
Exactly, yeah.
So,
sorry, I just wanted to tie in the two talks and understand what the big picture behind this was.
Yeah, thanks.
This is maybe a little bit left field. What I noticed one of your co-authors is Jade Master. She has also done some work on the algebraic path problem. Is that in the ballpark of any of this, or is that just a different?
I don't know. I don't know very much about it.
Not very.
Ladies and gentlemen, thank you very much. Thanks. I think next time is Andre Rodin. Thank you very much.
Thank you.
All right, cool.